Welcome to Jeremy's IT Lab. This is a complete course for the CCNP ENCOR, Enterprise Core exam. In this video, we'll move on from classic STP to cover its improved version, rapid-STP, or RSTP. Here's what we'll cover. First, we'll quickly compare classic STP and RSTP, taking a high-level overview of how they're similar and different. Then, we'll look at RSTP costs, which are used to calculate the switch's root cost. Specifically, there are two different ways of calculating port costs, short and long. We'll then cover the RSTP port states and roles, which are a bit different from those in classic STP. And then we'll cover the RSTP link types, which influence some aspects of a port's behavior. Let's get started. The ENCOR exam topics list only mentions RSTP and MSTP. So, why did we spend so many videos talking about classic STP? The reason is, the fundamentals of STP and RSTP are the same. Almost all of the information covered in the videos so far in this section applies to both STP and RSTP. The switches elect one root bridge. Each non-root switch selects one root port. One designated port is selected for each link, each collision domain. And the remaining ports are non-designated, or in RSTP, alternate or backup. And the STP tuning process is the same. The bridge priority, port cost, and port priority can be modified to change the STP topology. For example, determining which switch becomes the root bridge, which port becomes the root port, etc. And the same optional features in the STP toolkit can be used. Uplink fast and backbone fast-like functions are incorporated into RSTP itself, so they don't need to be configured. But port fast, BPDU guard, BPDU filter, root guard, and loop guard can all be configured, just like in classic STP. Of course, there are still plenty of differences between them, and they are what we'll cover over the next few videos. For example, port costs, states, and roles are different in STP and RSTP. And transitioning through those states is a different process. RSTP uses a negotiation or sync mechanism to speed up the move to the forwarding state. And topology changes are handled differently as well. We'll cover these differences over this video and the next few, but this section of the course will be shorter than the classic STP videos because we have already covered the fundamentals. First, let's take a look at RSTP port costs. Classic STP used 16-bit values, also called short costs. These are the familiar values shown in the chart. A cost of 100 for 10 megabits per second, 19 for 100 megabits per second, 4 for 1 gigabit per second, 2 for 10 gigabits per second, and no definitions for greater speeds. When STP was first developed, anything faster than 10 gig seemed impossible. Then, RSTP introduced the long cost calculation method, which uses 32-bit values to accommodate links of greater speeds. Here are those values. Remembering these values can be difficult, so I recommend picking one as a reference and memorizing it. For example, a 10 gigabit port has a cost of 2,000. Then, it's easy to calculate the others. Multiplying the speed by 10 to 100 gig divides the cost by 10, making it 200. And vice versa. Dividing the speed by 10 to 1 gig multiplies the cost by 10, making it 20,000. That's my recommendation, but you can just memorize them all if you prefer. Note that newer switches default to the long cost values, but older switches default to short, even when running RSTP. The switches in my home network, for example, use short costs by default. So, how can you configure a switch to use the long cost values? On my switch, I first used show spanning tree path cost method to verify the default, which is short in this case. Then I used spanning tree path cost method long to enable the long costs. Now it has changed to long. I typically prefer the short costs unless the long costs are needed. But if your LAN has very high speed links, you should use the long costs. Next, let's look at the RSTP port states. On the left are the classic STP states: blocking, listening, learning, and forwarding. There is disabled too, but that just means the port is disabled. It doesn't participate in STP at all, so I'm leaving it out. On the right side of the chart, we have the three RSTP port states: discarding, learning, and forwarding. So, RSTP combines the STP blocking and listening states into a single state called discarding. It serves the purpose of both. And that means it is both a transitional and stable state. Alternate and backup ports are stable in the discarding state. They don't forward or receive traffic. However, root and designated ports start in the discarding state, but transition through it to become stable in the forwarding state. So, what about the learning state? It's only used if the RSTP sync mechanism fails, and the port can't transition immediately from discarding to forwarding. Ideally, ports won't use this state, but will rather move straight to forwarding. We'll cover the RSTP sync mechanism in another video, so I won't explain the details here. Now let's see how a switch port transitions through the port states. First, let's review classic STP. When you first enable a Cisco switch port, you'll see that it's a designated port in the listening state. If the STP algorithm decides it will remain designated or become a root port, it will transition through listening and learning, spending 15 seconds in each, the forward delay timer. It will then be stable in the forwarding state. From any of these states, it can immediately move to the blocking state. For example, if a change in the STP topology makes it a non-designated port. And for a port in the blocking state to move to forwarding, it must transition through listening and learning. Okay, that's enough classic STP. We covered it in the previous videos. Let's see how RSTP works. When an RSTP port is first enabled, it is a designated port in the discarding state. If it is decided the port will be an alternate or backup port, it will remain in this state. But if the algorithm decides it will be a designated or root port, it moves to the forwarding state in one of two ways. Here's the big difference between STP and RSTP, and also the main benefit of RSTP. If the RSTP sync mechanism succeeds, the port moves immediately from discarding to forwarding. No need to wait for the forward delay time or transition through the learning state at all. But if the RSTP sync mechanism fails, the port spends 15 seconds in discarding and 15 seconds in learning, twice the forward delay timer, before moving to forwarding. In other words, it operates like a classic STP port, taking 30 seconds to move to forwarding. One example is if the port is connected to a switch that runs classic STP, not RSTP. In that case, the RSTP sync mechanism won't work. Like I said, we'll cover the sync mechanism in detail in a separate video, and talk more about the RSTP state transitions then. One final point. Like in classic STP, ports can move immediately to discarding if needed. For example, if there is a change in the STP topology. Let's move on to cover the RSTP port roles. The RSTP root and designated roles are the same as in STP. To review, a root port is a forwarding port that points toward the root bridge. It provides the switch's only active path to reach the root bridge, and each non-root switch must have one root port. And a designated port is a forwarding port that points away from the root bridge. All links, and by links I mean collision domains, must have exactly one designated port. So those roles are the same as in STP. Here's the difference. The non-designated role was divided into two separate roles: alternate and backup. An alternate port is an alternative to the switch's root port. It provides an alternate path toward the root bridge, and is ready to take over if the root port fails. Then, a backup port provides a backup path to the same link as a designated port on the same switch. Note that this will only occur if two ports on the same switch are connected to the same link, for example via a hub. Since hubs are almost never used these days, I wouldn't expect to see backup ports in real networks, but you should still understand the concept. Here's a simple network of two switches, each with two ports connected via a hub. I've already identified the root and designated ports. One of the remaining ports is alternate, and the other is backup. Which is which? The answer is, switch 2 G01 is alternate. It provides an alternate path for switch 2 to reach switch 1, the root bridge. and switch 1 G01 is backup. It provides another path for switch 1 to reach the same link as its G00 port, a designated port. Here's another way to identify alternate and backup ports. If a port is not root or designated, it is an alternate port if the switch is not the designated bridge for the link. Designated bridge is a new term. Basically, it means if the switch doesn't have the link's designated port, it is alternate. Switch 2 G01 isn't root or designated, and switch 2 doesn't have the designated port for this link, so G01 is alternate. And if a port is not root or designated, it is a backup port if the switch is the designated bridge for the link. Again, the designated bridge is the switch that has the link's designated port. Switch 1 G01 is not a root or designated port, and switch 1 is the designated bridge for the link. So switch 1 G01 is a backup port. Now that we've covered the port roles, let's review the STP algorithm, this time from an RSTP perspective. The process STP uses to create a loop-free topology is called the STP algorithm. RSTP's algorithm is nearly identical. The only difference is alternate and backup port selection. Here's a sample network for practice. I'm showing it now, but we'll walk through this network in this video's quiz. So there are three main steps in the algorithm: root bridge election, root port selection, and designated port selection. In classic STP, the remaining ports are all non-designated. But in RSTP, the remaining ports are either alternate or backup. And here are those rules that we just covered. Okay, so we'll look at this topology once more in this video's quiz, and confirm the role of each port. But before that, we have one more aspect of RSTP to cover. The final topic for today's video is the concept of RSTP link types. RSTP differentiates between three link types: point-to-point, shared, and edge. These determine some aspects of each link's behavior, or more specifically, the behavior of the ports connected to each link. The point-to-point link type is used by full duplex ports by default. These are the only ports that can take advantage of RSTP's sync mechanism to rapidly move to the forwarding state. To do so, they must be connected to another RSTP-enabled switch. The shared link type is used by half-duplex ports by default, ports connected to a hub. These ports cannot use the RSTP sync mechanism, so they will have to spend 30 seconds transitioning to the forwarding state, like a classic STP port. And then there are edge ports, which connect to end hosts and use portfast. These ports can't use the sync mechanism because they aren't connected to a switch. However, they are able to transition immediately to forwarding thanks to portfast. Edge ports can be considered a subtype of point-to-point and shared. If the port is full duplex, it will appear as point-to-point edge. And if it's half duplex, it will be shared edge in the output of show spanning tree. We'll confirm that in the lab video. Here's some practice now. Try to identify each of the link types in this network. And for edge ports, make sure to identify if it's point-to-point edge or shared edge. Pause the video if you want to do that, but now let's check. So first up, these are the point-to-point links, the only full duplex links. These are shared. They operate in half duplex. For the link between the two switches via the hub, I just put the icon over the hub. All four ports use the shared type. And these two ports are edge ports, connecting to end hosts. The one directly connecting to a PC is point-to-point edge, and the one connecting via a hub is shared edge. So those are the RSTP link types. We'll examine their behavior more in the lab video. Here's what we covered in this video. First, we briefly compared STP and RSTP. They are mostly similar, but of course there are important differences. We then covered short and long port costs, and then RSTP port states, roles, and link types. In the next few videos, we will cover some more RSTP concepts before moving on to multiple spanning tree protocol. Okay, now let's move on to the quiz. For today's quiz, identify the root bridge, role of each port, and type of each link in this network. Of course, this isn't a realistic LAN topology, but it should test your understanding of the different RSTP port and link types. And if a link uses the edge type, make sure to identify if it's point-to-point edge or shared edge. So pause the video now, grab a piece of paper, and try to figure it out. Okay, let's check. First up, switch 1 is the root bridge because it has the lowest bridge ID. Now, since we already covered the STP algorithm in a previous video, let's go through the root and designated ports quickly. Here are the root ports. Don't be fooled by switch 2's direct connection to the root bridge. It uses fast Ethernet, so it has a higher cost than its path via G00 or G01. And here are the designated ports, one per each link. Remember the algorithm. The port on the switch with the lowest root cost takes priority. If there's a tie, the port on the switch with the lowest bridge ID. And if that's tied, the lowest local port ID. Okay, now the rest of the ports are either alternate or backup. Let's go one link at a time. First, the connection between switch 1 and switch 3. Switch 1 G01 is backup because switch 1 is the designated bridge for the link. And switch 3 G01 is alternate because switch 3 isn't the designated bridge. Next, the switch 1 switch 2 link. Switch 2 F03 is alternate because switch 2 isn't the designated bridge. Next, the switch 3 switch 4 link. Switch 3 G03 is backup because switch 3 is the designated bridge for the link. And switch 4 G01 is alternate because it isn't the designated bridge. Finally, the switch 2 G01 to switch 4 G03 link. Switch 2 G01 is alternate because switch 2 isn't the designated bridge. Okay, we've identified all of the port roles. Finally, let's look at the link types. First up, all full duplex links are point-to-point. This includes direct connections between switches, and direct connections between a switch and an end host, like switch 4's F10 port. Next up, all half-duplex links are shared, links that connect to hubs. Don't expect to find hubs and shared links in real networks, but you should understand the concepts. Finally, switch 3 F10 and switch 4 F10 use the edge type. Switch 3 F10 is shared edge, because it connects to end hosts via a hub, and therefore operates in half-duplex. And switch 4 F10 is point-to-point edge, because it connects directly to an end host and operates in full duplex. Okay, we've identified all of the port and link types. That's all for the quiz and this video. I hope it was helpful. Thanks for watching. Before finishing this video, let me thank my JCNP level channel members. To become a member, please click the Join button under the video. Thanks to Jonathan Makara, Velva Jacob, George, Nasir Chowdhury, Gustavo Macedo, Marcel Lord, Pavel M., Dragos Hernea, Zakib Shah, Mayor Salman, Vitaus194, Chance Carter 56, Mark Jackson, Bold1C1U, Michael Carroll, Gerald Guillaume, Fristas 1207, Gabriel Braga, Hector Hernandez, Roji Kuriakos, Arpad Konives, 5 Feet, Owad Daniel Brown, Jose Alvarez, Hussein Yavuz, Kevin Hayes, Samuel Tavares, Roger Bratseth, Mustafa Ersoy, Nasser Zahar, Brian Grant, Georgi Gemejev, Hypocrisy Allergic, Arlen Plagaria, Dear Diso, Adelson Pereira, Farad69, Joyce Njoroge, Madmark 50484, Alexandru Stratan, Hiago Bicalho, DMJ2, Kurt Nell, Omid Farakesh, Steve Cox, Jasper Yim, Wilmer Romero, Pedro Hartman, Ivano Capuano, Enigma G, Jefferson Steelflex, Burl Campbell, Abhishek Sahu, Toxic, Sinan Sarisinar, Gio, Daniel Andrade, Mike Crumby, Eliel Eliluli, Jairo Francisco, Dragos George, Filip Jovanovic, Random User 7547, Wagner Botelho, ICT EDU Official, Mateusz Zashinsky, Dean I, Ruben Hernandez, Surge22, Girish Chitsinde, Trevor Goldman, and Abraham Mena. Sorry if I pronounced your name incorrectly, but thank you so much for your support. Thanks to you and my other supporters, I am able to make these videos and release them for free on YouTube, so I really appreciate the support. Another great way to support the channel is to like the video, leave a comment, subscribe, and most importantly, share this video with others. So if this video was helpful, I'd appreciate it if you did any of those. Thanks for watching.